All right, well, good afternoon, everyone. Thank you, Randy, for the opportunity to present here. So we're gonna present something different to what we have heard so far, and it's, as Randy has mentioned, it's the legacy to vision, the centralized protection timeline. So in the protection world, when we hear about centralized or centralization, it's kind of like a scary topic because protection is extremely important. As it has been mentioned here, we don't want to get the lights out. And that's why we're gonna just share with you what's going on out there on the rest of the world when it comes to protection relays and so on. So before doing so, let's take a synopsis of how protection has evolved throughout the years. And basically, the protection started with the fuses back in the middle of 1800s, which basically were used to protect lamps. Believe it or not, lamps were expensive at that time, so that's why fuses were used at that. Then they started being used to protect or to in the power system itself. Later on, we got the electromechanical relays in the early 1900s. What is electromechanical relay? So maybe some of you are still familiar with them. Some others, they have moved away from the electromechanical relays. But basically, the electromechanical relay does not require electricity, to energize the device itself, but it uses the electromagnetic principles to operate at contact output. And the contact output will drive the trip circuit breaker to isolate the fault. So one of the things that we can observe here is we needed multiple relays to protect a system. For example, if you have like A, B, C, a three-phase system, you will need to have one relay per phase. Also, depending on the number of elements, you might need to keep adding more. So the number of panels needed to protect a system was a reasonable number of panels compared to the ones that we see today. So then we got the microprocessor-based relays, but I want to mention between the electromechanical relays and the microprocessor-based relays, in the middle of 1900s, we had something called the solid-state relays. And the solid-state relays were basically using some electronic components to also now work using the same principal operations electromechanical relays to do the protection. Then we got in the early 1980s, the microprocessor-based relays. But when it comes to the microprocessor-based relays, one of the advantages is now we can see here on the slide the reduction of number of devices to protect the same system. So now rather than needing one relay per phase, it's going to be one single device to protect the system, like phase A, phase B, phase C, for your inverse time over current, your time over current rate, instantaneous over time over current, discharge protection, and so on. So that's basically what we got with the first generation of conventional relays. And what is the meaning of the conventional relays? That means we use the voltage and current that's coming from the instrument transformers in the substation in order for the relay to make the decision. And the response from the relay when something is detected and disturbance is detected is going to be a trip contact output to operate the call in a similar manner as electromechanical relays will do it. Later, we got the second generation of the protection relays. So the second generation, they are basically based on the IEC 6150 standard. What is the difference between the conventional and the IEC 6150 standard-based protection relays? So the difference is rather than having hardwired connections from the instrument transformers to the protection relay, so now we have digital signals providing the same information to the microprocessor-based relay. And rather than having a trip contact output to operate, now we have a digital packet, a digital signal to indicate the bay controller device in charge of operating the actual circuit breaker to open the breaker itself. So that's what we are familiar with. We know electromechanical relays, we know conventional microprocessor-based relays, and microprocessor-based relays using the IEC 6150 standard. Then we got the centralized protection, which is basically actually what we're talking about here on this presentation. What we can see here, we went from multiple boxes, multiple relays, all the way down to a single device. So this is where it comes like, how can I do that with one single box or one single device to do the same job that I was able to do with multiple electromechanical relays. So this is kind of like one big microprocessor-based relay with multiple protection elements, multiple overcurrents, distance, transformer differential, and so on in one device. So you can count it on the market. By the way, these are products available on the market to protect starting from 24 base all the way up, or some others a little bit less. So it depends on the vendor that you're working with. And just to continue with this, today we start talking about the virtual protection relay. Maybe for some of you, this looks like a little bit familiar. And this is a server. Yes, a similar server to what we have in data centers. Maybe you have heard the word of data center in the IT space, and that's true because the IT world, they have been using servers for many, many years. But it's something relatively new to the power industry because we are used to the electromechanical relays, microprocessor-based relays, and maybe some of the companies get into a centralized protection approach with a microprocessor-based relay, but now we are looking to this virtual protection relays, which basically resides in a computer server. Now, what is centralized protection and control? CPC. So as I've mentioned before, so basically the CPC is we take all of the multiple protection elements and have all of them available in a single device. So this is possible because of the standard, like the IEC 6150 standard, which allows the de-escalation of the potency current signals using something called sample values, and also for the trip signals using something called goose messages. So with this standard solution, now we are able to bring all of the data into the protection device and then utilize the multiple elements available inside of this microprocessor-based relay to do the same job the multiple microprocessor boxes will do in a substation. So this is the same hardware for every application for the entire substation. So that's basically what the centralized protection is all about. Now, why centralized protection and control? Why do you might want to consider centralized protection in your next substation project? Number one, it increases flexibility and adaptability. So what is the meaning of that? Traditional relays based architectures require physical rewiring or device replacement for changes. Maybe some of you might say, well, I'm able to do that with a microprocessor-based relay using IEC 6150. And that's true because we no longer have hardware connections if you are using IEC 6150. So that's something similar to what we are able to achieve with the second generation of microprocessor-based relays. Then we have the simplified engineering, commissioning, and maintenance. Now, this is, I think, one of the differences because rather than having to maintain or commission multiple devices, we are focusing in 1, 2, or maybe 3 for your entire substation. The improved performance through high-speed computing. No doubt, a computer server has a more powerful central processor unit or CPU compared to the microcontroller in a microprocessor-based relay. The algorithms are the same, by the way, because what we are doing in the microprocessor world is basically mimicking the algorithm, what the electromechanical relays have been doing for decades now in a logic in the microprocessor-based relay. The same logic that is available in the microprocessor-based relay is now brought into this computer server or microprocessor-based device that is used as a centralized protection device. Then we have a stronger cybersecurity posture. Why? Because you don't have to deal with multiple protection relays in your system to protect. Now you are focusing in 1, 2, or 3, depending on the type of redundancy that is designed with. Now, we have talked about like what is centralized protection and why you might want to look into centralized protection. But let's talk about like a little bit of history of the centralized protection and the virtual protection, automation, and control. So as we can see here on the slide, the concept is not new. It comes back from the early days of the computers. Back in 1969, George D. Rockefeller proposed this on his paper published called Fault Protection with a Digital Computer. So basically, this paper is the result of his Master of Science thesis, where he proposed to protect the system using a computer. Now, one of the conclusions of this study is the author did not find anything that can basically restrain the computer to use as a protection device in a substation. Now, I want to highlight Mr. Rockefeller mentioned on his paper that this is basically a study, not necessarily an implementation at that time. So then we have Westinghouse. Westinghouse Electric Corporation project in the United States basically prepared a substation specification requirement for the Electric Power Research Institute. And this was to protect basically the bus bar protection, shunt reactor, out step, break failure protection, and also controlling automation was included as part of this proposal and project. So this was developed and deployed in a few substations back in the 1980s. Then the next project that we have here in our history is the SIPSOR system in Spain. So this was developed by GE in the Northwest utility in Spain, and it's a single hardware package that consists of 2 in-camera feeders at 66 kilovolts and 5 feeders in the 15 kilovolts. So then we have the Ontario Hydro. Today it's Hydro 1, put in service the first integrated power automation control system, the IPAC, in more than 100 substations. So the computer system with all the protection, control, and monitoring was used. Just a second here, something I have on my way. Was as computer system with all protection, control, monitoring, recording for a dual element SPAD network at the station. So the dual element SPAD network station is a transformer station to step down voltage from transmission to distribution levels. So 56 of these IPACs were built and put in service before the project was abandoned in 1998. So far we can see the concept started back in 1968, and now we start seeing throughout history that some of these centralized projects start being in service or as pilot projects. Then we have the button-false L distribution. So in collaboration with ABB, this utility company developed a CP system for the island of Gotland. All protection and control algorithms using a real-time kernel with an embedded Windows operating system. This basically runs on a standard industrial computer, and it connects to 5 racks for analog and inputs and outputs. Basically, the signals were gathered to the centralized unit for the protection purpose. Then the last one that we have here on this history summary is the SA sensor project, which was developed together with Alinder by Locomation. So Alinder is a utility company in the Netherlands, and Locomation today is called the Grid-to-Grid company. They developed some sensors to utilize the current voltage and breaker interface modules for digitalization of process bus data and a redundant centralized computer unit running a proprietary real-time operating system. So it was not like a standard as 86950. There were multiple pilot projects deployed from 2004 to 2010, 10 in total. And in 2011, approximately 200 installations rolled out, and more than 100 of these pilot projects or deployments are still in operation today in multiple utilities in the Netherlands. So as we can see here, we start from the concept all the way to real projects especially in Europe, where basically show how the centralized protection can do what multiple devices are able to do in a typical microprocessor-based substation. So what does the community from IEEE and IEC says about it? What has been done so far from the standardization perspective? So starting with IEEE, the IEEE released last, 2 years, the C37.300 guide. This is a guide for centralized protection and control systems within a substation. So the guide shows multiple options for you to consider in a centralized protection approach. and also some analysis of advantages or disadvantages which for each one of them. So it's a really good document for you to read. If you are interested, you can find it on IEEE Explorer. Then we have from IEEE, the PSR Protection System Relay Control Group released a report, which was the working group K15. Actually, the work of the PSR, the working group 15, was the base for this guide that was released in 2024. This is a document that you can find online. If you just Google for Centralized Substation Protection Control Report, you will be able to find it and read it. It has really good documentation. The guide is the next step to the report. Then today we have the IEEE from the power system communication and control community. We have the working group P21, which is basically working on the roadmap for developing new or updating existing IEEE standards to address issues of centralized protection and control system. So it is a review of the standards or what else might be needed for CPC. That's still, the work is still ongoing. It's a joint effort with the PSRC working group I-49. Then on the other side of the world, we have SIGRE. And SIGRE released the technical brochure A91 called Protection, Automation, and Control Architectures with Functionality Independent of Hardware. Basically, this technical brochure provides detailed roadmap for transitioning the electric power industry towards virtualized hardware, independent path architectures, and the findings are positioned as foundational for future standardization and innovation within digital substations and grid automation. So this is a document available today from the SIGRE perspective related to virtualization. And then we have an ongoing effort from SIGRE Working Group B584, which is basically recommendation and constraints for development and interfacing of virtual intelligent electronic device implemented in protection, automation, and control systems. So this working group aims to describe the possibilities and requirements for the virtual intelligent electronic devices and the hosting server structure, and to illustrate this with use cases. Basically, what is needed from the server to host multiple virtual protection relays. So we have talked about virtual protection relays so far, but I'm going to explain that in the next later. But let's focus now on the CPC-based system architectures. So this is an extract from what was presented on the working group H45 that was responsible for the guide that I mentioned on the previous slide. Three of the multiple architectures are highlighted in this presentation. The first one is the type 1. Let's take a close look of this picture here, or this image here, where we have the centralized device. But notice that the centralized device is used as a backup because we have the microprocessor-based relays getting the data from the instrument transformers in an analog format, but the same microprocessor-based relays are basically digitalizing the signal and making that available for the backup CPC system. So we can see multiple microprocessor-based relays and one backup system, a centralized protection. The next one is the type 3A architecture. On this one, we have multiple process interface units. What is a process interface unit? So the process interface unit basically takes the voices and current signal, digitalize the information, but also serves for control purposes. So it digitalizes the signal, and now it makes it available to a system A and system B. What we can observe on this image, we can observe that each process interface unit is basically providing the information to the respective system, because we have a system A and system B. So one process interface unit per system. We have multiple devices compared to the previous approach on the type 1. Now, we have the type 5A system architecture. In the type 5A, we have like A and B process interface unit, but feeding a line A and B Ethernet network. So rather than having a point-to-point communication as it was on the previous one, now we have a centralized bus, the process bus, for LAN A and LAN B, and provide that information to the system A and system B. Now, the analysis that we can see and find on this from this presentation and that was made by the working group H45 that I was part of is that the type 1 has an availability like type 3A and type 5, but its reliability is lower. So what is the meaning of availability? So basically describes the readiness of the protection system to operate at any given time. And what do I mean by reliability? It's the probability of the system performing its purpose adequately for the period of time intended under the operating conditions encountered. So the type 1, the first one, the type 1, looks simpler, but the reliability is among the slowest ones of the multiple architectures analyzed by the working group or that are available in the guide. So the one that has the highest score, or among the highest score, is actually this one. But we can see that we need more devices compared to the 5A. So 5A has a reliability a little bit lower compared to the other one, the 3A, but we can see the reduction of devices compared to the other. So that's from the CPC-based system architecture. Now, do you have an idea when we talk about centralized protection? It's a matter how I'm going to design my system in order to make it available and reliable. So what are the considerations? So this is exactly what I meant. So reliable and availability. We have an idea based on the 3 examples that I have provided here. Now, maintainability. That's something that you have to take into consideration. So the CPC system is designed for easy maintenance. That's the whole idea of having one device, including hardware and software upgrades for the CPC system, because from time to time, you need to perform some firmware upgrades. So it needs to have the capability to replace a complete CPC system, including the hardware and software upgrades without any shutdown requirements of the system components. Believe it or not, that's something very common in the IT world. They can take a system like change hard drives, they can change the server, everything in hot without taking any outages. So that experience can be taken into the power industry as well. The scalability and flexibility, that is another topic that you have to take into consideration at the time of the design of the CPC system. Basically, the scalability refers to the extension of the capability of the CPC system, such as accommodating more feeders than planning a substation by upgrading systems hardware, software, or both. The flexibility also refers to the use of features available in a system based on changed system needs, such as the use of distance protection instead of directional protection. So what I'm going to need down the road, if I already have commissioned this device, how am I going to add it? So we have to take that into account at the time of the design. What about interoperability? Well, if you are familiar with IEC 6150 standard, if a company or a vendor says it's IEC 6150 standard compliance, that means you can automatically assume if you buy a process interface unit from one vendor and you buy a centralized protection from a different vendor, they're going to work because they're based on the IEC 6150 standard. Then we have testability. This is one of the questions that we get from time to time when I talk about this topic, because we are so used to testing electromechanical relays, to test microprocessor-based relays, solid-state relays, but how do I test the centralized protection or virtual protection? So we have to take testing into account. So the architecture of the CPC-based system could impact how the CPC-based system is tested. So do you want to include maybe a goose message for testing purposes, or you don't want to include a goose message for testing purposes, just work with the one that is going to be for the actual operation? By the way, I just want to emphasize again, the goose message is in the IEC 6150 is the digitalization of the binary inputs and binary outputs in the microprocessor-based relay. So that means today, if I'm testing a microprocessor-based relay, and I want to test a specific element, I can use a spare contact couple to make sure that's the only element operating, nothing else getting on the way when I verify the operation. That's an element testing approach. So something similar can be done here if we take testing into consideration when we're designing the CPC system. Then let's make like a parenthesis here before getting more into virtualization. So what is virtualization? And in virtualization, we're going to hear something about hypervisor. And what is a hypervisor? So if you remember when we got the migration from Windows XP to Windows Vista or Windows 7, I recall that the computers automatically came with a virtual machine. And reason why is because some of the computer programs that were working fine on Windows XP require now needed to work on Windows in the newer version of Windows, but they didn't work. So they require a virtual machine with Windows XP running in a newer version of Windows to do the same thing. So two basically operating systems and one piece of hardware. So that's what we know as hypervisor type 2. And we have the hardware, which is your regular computer, just to make the analogy, the traditional operating system, which is going to be Windows, and then you have the multiple applications. So the type 2 hypervisor is not a real-time operating system. So we cannot use that type of hypervisor in the protection because we need to have a real-time operating system to guarantee operation of the correct operation of the protection elements. So that's why type 1 hypervisors offers that, because we have basically the hardware. In this particular case, the hardware is going to be the server. In the server, we're going to have the hypervisor, which is equivalent to the operating system. The hypervisor is basically in charge of allocating the multiple resources for the multiple virtual machines that we can see here. So how many virtual machines I can have? It depends how many the hardware it's capable of. So here we can have multiple virtual machines with multiple operating systems applications individually running on the same hardware. So now in this other example here, we can see we have the first virtual machine with 4 CPU cores. How many CPU cores can you have in one server? It depends what you pick. Do you select a fanless server or you select one with fans? So each one of them has pros and cons, because the one with fans, it can handle just a specific number or can have a CPU with a smaller number of cores compared to one with fans with a bigger number of cores. Believe it or not, today the technology has evolved, and now even the fanless device are capable to provide more cores in a single CPU. So it depends which one you are selecting when it comes to the hardware, how many virtual machines you're going to be capable to install. So in this example, we have another virtual machine with just 1 core and another one with 16 cores and so on. So now you can have the idea like each virtual machine is going to have the respective memory, RAM requirements, storage, CPU cores, even networking part, how many Ethernet networks from the server I'm going to need for this, and so on. Now, moving to the protection side, this is what I'm talking about, like when it comes to the hypervisor and the virtual machines. So in the conventional architecture, this is basically a microprocessor-based relay or a centralized protection running in a microprocessor-based device. We have the hardware or the server, the conventional operating system, and then the applications. So you cannot have more than that, because the device or the application that is running here is designed to run in one single device. Now, in the virtualized architecture, we have one server hardware, which is going to use a hypervisor type 1 with multiple virtual machines. So now the virtual machine, it's going to be your virtual protection relay. So now you have your centralized protection in a virtual environment, and you can have multiple of them in one piece of hardware or one server. So now you can have multiple centralized protection or multiple virtual relays, and also you can have multiple servers in your substation for backup purposes, maybe a hot or hot standby. It depends how you design it. So there are commercially available CPC and VPAC products that offer hardware or software-based packets. I just want to highlight that because you can buy a centralized protection as like a similar looking to the microprocessor-based relay, or you can buy a centralized protection in a virtual environment. Now we have here some conventional versus CPC VPAC comparison. So what do I mean by conventional? That's basically the microprocessor-based relay. Basically, we have the asset management. How is the asset management in the conventional world? I have to handle multiple relays, multiple microprocessor-based relays. How is the asset management in the CPC or VPAC? We have a few number of CPC systems that I have to manage. What about the device managed? When it comes to firmware upgrades or software upgrades, it's multiple devices that I have. First, I need to know where they are in my system and how many of them they need an upgrade. In the centralized device, it's one device. Now I know where it is, and I have to keep record of so many of them in the system. For maintenance, how many days does it take me today to test one single microprocessor-based relay? So now, how many days do I need to test my centralized protection? Because it's one device with the entire protection device in the substation. Security, similarly to what I highlighted before, one of the advantages of the CPC is a reduced number of devices with fewer access points versus the conventional where we have multiple devices. Interoperability, well, in the conventional world, it could be challenging if you are using multiple vendors. And the CPCB system, since it's one device, IEC 650 standard, pretty much interoperable. Then we have substation master interface. Maybe you might not have such in the conventional, but it's possible to do it in the CPC VPAC. And aggregation functionalities in the conventional, it's possible. In the CPC system, it depends how you have chosen the philosophy and technology when you did your design and architecture. So now we have touched and talked about centralized protection, virtual protection, but one of the things that you're going to find out there is an alliance that started with multiple OEMs and utility companies called the VPAC Alliance. The VPAC Alliance vision is to accelerate the specification for substation digitalization throughout the writing multiple documents for cybersecurity, hardware requirements, application requirements, so on, for basically users like you to be able to learn more about it and make your decision when it comes to virtual protection, automation, and control. The Alliance was launched in 2023, and today is going through a new reorganization as a non-profit organization. So if you work for a utility company and you would like to join the Alliance, you are more than welcome to apply for it, and now it's the right time to do it. Then we heard about in the history of the multiple projects, especially in Europe, when it comes to centralized protection from many years ago. But let me share with you one project here in the United States. And this project comes from Salt River Project, SRP. Salt River Project, SRP, it's a water and electric power delivery utility located in Arizona, which basically is a non-for-profit organization. They have strong goals of cost reliability, affordability, and sustainability, and they strongly believe in innovation. So SRP came with the need of updating multiple substations to maintain the low growth in short period of time, on the top of basically replacing the existing relays out there. So SRP has been had a strong belief like virtual protection relays was the way for them to achieve their goal of replacing the existing microprocessor-based relays, electromechanical relays, and also building new substations in a shorter period of time. So this is basically the present of SRP. We can see multiple devices. By the way, SRP start working with or exploring the centralized protection approach before they jump into the virtual protection approach. So this utility company has been doing this for many years. and they have been gathering information throughout it. But now they do see that virtual protection relay is the way to go because they even get some more savings compared to the centralized protection that I have mentioned on the previous slides. So this is the future for them. Now they have redundant merging units with multiple servers for redundancy purposes and multiple applications of virtual machines running on the servers so they can simplify the substation automation control. Now, what are the barriers for adoption? Well, one of the first things that you might want to ask yourself is, why am I want to move to IEC 6150 to begin with? What are the advantages of the IEC 6150 standard? And why am I want to move to centralized protection or even virtual protection relay? As I've shared before, the biggest justification that I see by talking to multiple utility companies is time. Time to develop protection application systems and build substations in a faster way. At the same time, reducing the amount of panels needed for those new projects or new substations. So the other challenge that we encounter here is if you are currently working with microprocessor-based relays using hardwire connections, the move from there to virtual protection relays or centralized protection is big because you have to learn first about IEC 6150 and then get used to the new approach of designing all protection in one single device. There are advantages. For example, break and failure protection. You don't have to worry about coordinating multiple devices because everything is on the same device. When it comes to virtual protection, there are different flavors. And I want to highlight that because on the market now you find 2 vendors, and you will find more than 2 vendors in the near future. One of the vendors has taken the centralized protection approach. I mean, one IED, intelligent electronic device, for the entire substation, many protection elements in one device, and the other vendor has taken a separate approach, which is basically virtualizing every single microprocessor-based relay in your substation in a virtual machine. So then the approach is not that different from the one that you used to with the microprocessor-based relay, but it still is a centralized approach because it resides on one server or one piece of hardware. The other things for the barriers for adoption is knowledge. So how many of you now are familiar with Ethernet switches, communication? Because in the protection world, that's where we don't really deal with that. But when you're moving to digitalization, we have to start learning at least the basics of communications. I know we have a department in the utility company who are the experts for that. But as a protection engineer, you might want to maybe take ownership of your switches that are going to have your trip signals and voices and current signals in a digital format. So the VPAC projects around the world projects, here is just a summary. We can see Southern California, Edison. They are a strong also belief on virtual protection relays. They are very active on the VPAC Alliance. They have completed the research projects. Now they're waiting for a field deployment for this virtual protection relay technology. Then we have Southern Company in the US. They start talking and sharing their findings back in 2024. And Techville R&D in Russia, basically this is an engineering firm specializing in digital substations, relay protections, and IEC 650 technologies. They're recognized in the Russian power industry for the advanced R&D and practical engineering solutions, and they have commissioning CPC systems since 2018. Then we have the Caruna project in Finland. This distributed system operator pilot and test a virtual protection control automation solution in real life substation from 2021 to 2023. So then we have the UK Power Networks with the Constellation project, which basically includes a virtualization, centralized protection concept in a laboratory test in 2023. But actually, a couple of weeks ago, this UK Power shared their follow-up of this project, which basically they're taking it to the next levels. So what is the future heading to? So the rapid load growth demands faster engineering and substation deployment. You can see this is basically the number one justification for utility companies to look into centralization and virtual protection relay. And expect the protection automation control personnel to need to work closer together and require education to learn IT basics, as well as non-typical collaboration with other departments. We need to learn about Ethernet networking. We need to learn a little bit more about virtualization. So this is the future, and we cannot stop it. We like it or not, if we are afraid, the best way to overcome a fear is to start doing your research, do your homework, build a laboratory. In the laboratory, you're going to learn more about it. You're going to train your field personnel how to use this, how to test it. And also with your laboratory, you can basically also take what's happening in the field and mimic it. What happened maybe for a fault, and recreate it and find what did go wrong without the need for you to be scratching your head. What did go wrong in the field? Because now I have everything on my lab and I can just play it back as many times as I want.